Hello dear learners, in this class and in this video we will talk about the moving boundary method to determine the transport number. Now this video is in continuation with the Hittov's method where we have talked about one way of determining the transport number. In this method, this is the second video. Here also we are going to form and will try to solve how to calculate the transport number in an alternative method. And this method is also referred to as the moving boundary method. So now, what is the meaning of moving boundary here? How this method works? What are the constituents of this method? All of that we are going to discuss one by one. And finally, we are going to derive out the formula that how can we solve it to calculate the transport number. So basically, this is a experimental setup of the moving boundary method. In this setup, one thing is very evident that there are two solutions here in this setup, this yellow colored solution and then this blue colored solution. This yellow colored solution is HCl solution and the blue colored solution is cadmium chloride solution. They are placed in this way. Then there is one of the electrode here, that is the cathode, and this cathode is generally made up of platinum, and here we have the anode, and this anode is made up of cadmium itself. So the cadmium chloride solution is here, the HCl solution, then we have the platinum, then we have the cadmium, and here also we have the battery connected externally and also one of the coulometers connected to determine that how can we like what is the amount of charge which is carried by the particular solution. So now what happens here? So basically, in this particular setup, the HCl and cadmium chloride solutions are used, and we are mainly concerned with this HCl solution and basically with the H plus ions. Means we have to find out the transport number of H plus ions. Means the whenever this circuit is connected and this circuit is closed, the current will flow. The current, supposedly the current starts flowing. Now this current, as it is flowing, it will move like this way, and in from this solution also there will be the conduction of electricity. Now basically we need to find that how much amount of electricity was actually carried by the H plus ions. That is what is the main aim of this moving boundary method. Now there is one of the important questions which come in exam, that why are we choosing the cadmium chloride solution here. Now when we compare HCl solution and when we compare the cadmium chloride solution, this cadmium chloride solution has more molecular weight and it is comparatively heavy. It is comparatively heavy and it is more density. So it tends to settle down. And the H plus ions and this HCl, it is less denser as compared to cadmium chloride, so it will float over the cadmium chloride. Now when it will be floating over the cadmium chloride, there will be the interrim or a boundary which will be formed between the hydrochloride solution and the cadmium chloride solution. Now this boundary is what is present because of the density differences. Now once the circuit is closed and the current starts flowing, this current, as it passes through here from this way, this particular boundary starts shifting upwards. And with this shift in boundary, we can actually determine that how much amount of current was carried by the protons or the H plus ions. Now the experimental setup is quite simple here, and this boundary movement, now I have to explain you that why does this movement happens of the solutions. See, basically here we have the cathode. Now cathode is negatively charged. Now this cathode will be competed by the two of the ions, that is either the hydrogen ions or the protons, or there can be the cadmium ions. Now I already told you that the cadmium ions are comparatively denser, so they will move slowly, and the hydrogen ions are comparatively lighter, so they can move fastly. So whenever the current is trying to move and whenever the current will be carried out by these electrolytes, the mobility of H plus ions will be more than the mobility of the cadmium ions, because of which the H plus ions tend to move more faster and reach towards the cathode and get discharged there. Now as the cathode has the H plus ions discharged, the equal amount of chloride ions will also have to discharge towards the anode so that the current can flow. Now this chloride ions are provided generally by this cadmium chloride. So cadmium chloride here has many functions. One of the important functions is that it is helping to form the boundary because of the density differences. Secondly, the cadmium ions will move slower and hence we can easily determine the transport number of protons, because only the protons will be the first who will reach and will discharge at the cathode. Thirdly, the cadmium chloride solution also provides abundant chloride ions which will equally discharge at anode as the protons are discharging at the cathode. When the discharging happens, that time the current will be flowing. Now let us take an imaginary situation where the current has started to flow and the H plus ions have moved and they have started to discharge at the cathode. In that condition, the HCl solution will tend to move upwards. Now suppose here it has moved this much amount of length. Now let us say from AA it has moved to BB dash, or AA dash it has moved to BB dash. Now let's say this is L centimeter, means the distance which is traveled by the boundary is approximately L centimeter. So we can see here that the distance which was traveled by the boundary was L centimeter, and let us say that the area is A centimeter square. So how much volume was utilized here, or how much volume did actually move? It was L into A centimeter cube. As simple as that. Now we know that what is the formula of concentration. The concentration of H plus ions, or molarity of H plus ions, or normality, let's say here normality, it is nothing but it is the equivalent weight of that particular substance upon the volume, right? So here if I want to find out the equivalent weight will be equal to the concentration of H plus ions multiplied by the volume. The volume is already A centimeter cube and the concentration, let's assume it to be C. This will be the equivalents of the H plus ions. Now always remember that for the protons, one equivalent will carry 1 Faraday of charge. So this equivalent is actually nothing but the Faradays, and this is very specific for the H plus ions, and this has been proposed by Faraday that one equivalent of the H plus ions will carry 1 Faraday of charge. Now suppose here we were having n equivalents, so it must have n Faraday of charge, right? So this n Faraday of charge will be equal to the concentration of the H plus ions multiplied by A, and the centimeter cube we can convert into liters by dividing by 1000, because 1 liter, it will be having how much? It will be having 1000 centimeter cube. Now suppose we are considering only 1 gram equivalent here, so 1 Faraday will be there. So 1 Faraday is equals to concentration of that H plus ions multiplied by A into L upon 1000. Now what is the formula of transport number? Transport number is nothing but the charge which was carried by the H plus ions upon the total charge. Now let us say that the total charge here detected by coulometer is Q, and the charge carried by H plus ions is what we have determined here, this one. So the formula is very clear here that the transport number will be equal to, like, the transport number of H plus ions will be equal to the charge which was carried by the H plus ions, and that is nothing but the concentration of H plus ions multiplied by the area multiplied by the length, that is equal to volume itself upon 1000 multiplied by the total charge. This total charge is Q, so I can say that this Q is the total charge. So as simple as that, we have easily found that how we can determine the transport number of H plus ions here. Only things which are required here is coulometer. If the coulometer will be present, the coulometer will determine that how much of the total charge is present here and how much of the total charge has flowed. This H plus concentration will be well known through this HCl solution itself. Suppose we are taking 0.1 molar or whatever, we can easily find out the H plus concentration and it will be already known. This area and length, area is standard. See, area will be always standard because of this particular vessel. There will be a fixed area of that cross section. Now this we can easily determine. If the radius is present, then we can determine it by pi r square. The area would be known, and the length is the most important factor here, because whatever will be the length carried, whatever will be the length which has moved by this particular boundary, that will be coming here in this value. Then this Q I have already told you, and divided by 1000, because here this volume we are calculating in liters. So that is how we can determine the transport number of protons. So from here also one more relation we can find is that the transport number of protons will be directly proportional to the length which is moved by the boundary. See, more the moving of the length, more will be the transport number of the protons. As we can see, it is evident in this formula also. So that is how there is this another method which is called as the moving boundary method, and it is used to determine the transport number of the protons.